Next topic. Hello student friends. Types of voids and classification of ionic structures. Now when you learn about ionic structure, the first thing that we like to summarize all the types of voids. Trigonal void is the smallest void with the size of 0.155 times of r, where capital R stands for radius of the sphere and small r stands for radius of the sphere which exactly fits into that void. Similarly, tetrahedral void is 0.225 times of r, octahedral void is 0.414 times of an r, and cubic void is 0.732 times of a r. So, we know which void is the largest. The largest void is cubic void and the smallest void is trigonal void. Now when you go to the next part of ionic structures, remember, right, any ionic compound like NaCl, then we know Cl minus is a larger ion. Now we will consider larger ion as lattice points. I suppose you remember the word lattice points. It will make up the packing like FCC, HCP and so on, and Na plus as per its size will go to one of this void as per its size. So, if the size is very small, it will go into trigonal void. If the size is very large, it will go into cubic void. That is what you should be thinking about ionic structures. So, now before we go to ionic structure, this is a small numerical that we can think of and solve. Now, how you are supposed to solve this numerical? Oxide ions are arranged in HCP. If oxide ions are arranged in HCP, you know oxide ions. Why? They are making up HCP because they are larger in the size and therefore, they are making up HCP. So, they will be how much in number? HCP means 6 in number, that is a rank. Then aluminum ions occupy 2/3 of octahedral voids. Now, why aluminum is going into octahedral void? Because aluminum is smaller size ions go into void and larger size ions go into packing or lattice points. So, what are octahedral voids? 2/3 of octahedral voids. How many octahedral voids are present in HCP? 6 only, because we know if number of spheres are Z, number of octahedral void is also Z. So, Z is 6, number of octahedral void is also 6. 2/3 of that is aluminium. If 2/3 of that is aluminium, that means aluminium is 4. So, what is the formula? Aluminium will be 4, oxygen will be 6. So, if you simplify, it will be Al2O3, and that is what we really know. Aluminium oxide has a formula of Al2O3. Now, we have realized that oxides makes up CCP or HCP, sorry. They make up HCP, and actually aluminum ions are occupying voids. Which void? Octahedral voids. Are they occupying all the octahedral voids? No, they are occupying 2/3 octahedral voids. But why they occupy 2/3 octahedral voids only? Why not all? So as to have total charge 0. You know, aluminum charge and oxide charge, if you add all the charge should be 0, because any unit cell should be electrically neutral. That is the reason how this type of arrangement is there. Now, classification of ionic structures. In ionic structure, there are cations as well as anions. Then you know larger of these two ions is anion, that will occupy lattice point. When you say the word lattice point, that means they will either make up AAA packing like SCC, or they will make up AB packing like HCP, or they will make up ABCA packing, that is FCC. And where do you expect cation will go? It will go into voids. It will go into voids. And the size of cation to that of size of anion, that is a radius ratio, will decide our cation will go into which void. Now, if your cation size as compared to anion size, now those who want to know, R plus upon R minus can be remembered as R upon R also, where R was the size of the void and capital R was nothing but the radius of the sphere making up that void. You remember, this is trigonal void ka size, this is tetrahedral void ka size. So, if your size is lying between trigonal void to tetrahedral void, it will go into trigonal void. How come? it is said like this: if you have this type of an arrangement, if this is the case, this is how trigonal void will be there. Imagine our void is slightly bigger than trigonal void, imagine like this. Still it will try to fit into our trigonal void only by creating some amount of space. Are you able to see? It will create some amount of space, but still will try to remain in trigonal void. What is the advantage of remaining in trigonal void? It will be still touching the surrounding spheres. Now you should know this is now your cation, this is now your anion. If they touch each other, electrostatic force of attraction will be highest. So to keep electrostatic force of attraction highest, cation will still go into trigonal void. Only thing is, right, anion will have space between them. That's good now if they have anion space, because anion will have a repulsion. That repulsion will be less. So although the size of the cation is slightly bigger than trigonal void, still it will go into trigonal void with coordination number of 3. Now we don't have a very good example available under trigonal void of any ionic compound. If your size lies between tetrahedral void and octahedral void, remember it will go into tetrahedral void. Now, right, although the size is slightly bigger than tetrahedral void, why still it is going into tetrahedral void? Because it will still touch cation, and if anion and cation touch each other, the electrostatic force of attraction will be largest. In tetrahedral void, coordination number is 4. Example is zinc sulfide. In zinc sulfide, sulfide makes up CCP or FCC, and zinc ions occupy tetrahedral void. That is what we want to say. If you have size radius ratio between octahedral void and cubic void, will remain in octahedral void with coordination number of 6. Example is NaCl, where Cl minus makes up lattice points of FCC and Na plus makes up octahedral void, like this. Coming to the next one, if your radius ratio lies between cubic void and the size of the spheres around, then go into cubic void with coordination number of 8. Example is cesium chloride, where chloride makes up SCC. Those who want to know SCC, A packing, and cesium will occupy cubic void. Cubic void can be imagined like a body center. So imagine Cl minus making up 8 corners and cesium making up cubic void or body center. So that is about learning of ionic structures. So in ionic structures, remember, anions make up what? Anions make up lattice points. And where does cations go? Cation go into void. Which void? Which void is decided by a radius ratio. So if the radius ratio is small, that means cation size is very small, then cation will go into smaller void. If radius ratio is large, that means cation size is large, then cation will go into slightly bigger void, and so on. You know, trigonal void is smaller and the largest void is cubic void. So that was basic information about ionic structures. We'll stop here only. Solid state, next part, types of ionic structures. Now this entire types of ionic structure is not given in state board syllabus, and it is also not given in NCERT, but it has been found there are many MCQs which are asked in medical entrance exam like NEET and engineering entrance exam like JEE. Under this ionic structure, 5 ionic structures are to be learned compulsorily, along with learning of one covalent structure called as diamond. So we come to the first structure, NaCl, which is also called as rock salt structure. So if you come to discussion of rock salt structure, NaCl is also called as rock salt structure. It has been found the radius ratio, that is the size of cation to the size of anion, is found to be 0.52. Now if you know, this 0.52 lies in the range of 0.414 to 0.732. That means Na plus will occupy octahedral void, and we know octahedral void is a speciality of FCC type of a backing. That means if Na plus is present in octahedral void, there is other ion making up FCC. Who is other ion? The other ion is Cl minus. That means Cl minus will occupy FCC and will have a rank of 4. That is a characteristic of FCC. Those who want to know, when I say it occupies FCC, that means it will occupy 8 corners and 6 face centers. And when somebody says it occupies octahedral void, that means it will occupy body center and edge center. That is what we understand. From where all this understanding has come up? From the experimental data that the radius of cation to that of the radius of anion is found to be 0.52, and that radius ratio lies in this range. Therefore, Na plus occupies octahedral void, and we know octahedral void and tetrahedral void are speciality of FCC and HCP. Everywhere we are taking cube as a standard. Therefore, we are going to take FCC as a standard. Therefore, Cl minus will occupy FCC and will have a rank of 4. When I say it will have a rank of 4, that means 4 chloride ions will make up one unit cell. That means 8 corners and 6 face centers of Cl minus will make up 4 chloride ions apparently. This is what is the structure that you see, where the green color sphere is Cl minus. You can clearly observe it makes up corners, and makes up face centers. And where is Na plus ion? Na plus ion is making edge center and is making a body center. But why Na plus ions makes edge center and body center? Because Na plus is occupying octahedral void, and octahedral void's position is edge center and body center. How many Na plus ions will be present? That is the next question that we have. We are aware there are 4 chloride ions and any unit cell should have 0 charge. So, how many Na plus ions should be present? Clearly 4 Na plus ions should be present. So, to balance, right, 4 chloride ions, 4 Na plus ions should be present. That means rank is 4, and we are aware that an FCC is made up of only 4 octahedral voids. So, 4 Na plus 4 octahedral void, that means Na plus occupies 100% octahedral void. That is what we understand and we learn. Conclusion. Right, conclusion is Cl minus makes up 8 corners and 6 face centers, which stand for 4 chloride ions as per contribution, and Na plus occupies 12 edge centers and 1 body center, that is octahedral void, which stands for 4 Na plus ions. That means Na plus ions occupy 100% octahedral void. That means tetrahedral void is 0% occupied by anyone. That is what is NaCl structure or rock salt structure. So, we have 4 Cl minus ions and 4 Na plus ions. That means it is made up of 4 NaCl units. Ionic units are also called as formula units. So, conclusion is, right, formula per unit cell is Na4Cl4 simplified as NaCl, and number of NaCl in one unit cell is 4. So, we say rank for NaCl is 4. Rank for Cl minus is 4, rank for Na plus is 4, rank for NaCl is also 4. This is what we understand. There is one more thing that we would like to understand in NaCl structure only. What is that? That we like to understand in NaCl structure. In NaCl structure, one more thing that we like to understand, if you take this corner is occupied by Cl minus, this corner is also occupied by Cl minus, and the edge center, that's octahedral void, is occupied by Na plus. So, if you know this is R minus because it is the size of anion, this is R plus and this is also R plus and this is R minus, and from here to here, that is from here to here, it is edge length. You got this? This is ball stick model. In reality it is Cl minus is this much size. In reality Cl minus is this much size. This is Cl minus, and inside size is who? Na plus. This is Na plus. This is Cl minus, which are bigger spheres, and smaller sphere is Na plus, and they actually make up edge length A. That means R minus plus R plus plus R plus R minus R plus R plus R minus will be equal to A. That means 2 into R plus plus R minus is equal to A. Therefore, R plus plus R minus is A by 2. That is what is the calculation that we understand for NaCl, which is a rock salt structure. Now, one more thing that you should know, Na plus occupies octahedral void. Anyone who occupies octahedral void has coordination number of 6, and Cl minus, if you calculate Cl minus, it will be also surrounded by 6 Na plus. So, coordination number of Cl minus is also 6. Na plus surrounded by 6 Cl minus, Cl minus surrounded by 6 Na plus. So, coordination number of Na plus is 6, coordination number of Cl minus is 6. Therefore, NaCl is called as 6:6 ionic solid. We go to zinc blend structure or zinc sulfide structure, and the data which is available is this one. What is the data available? Experimentally, size of zinc to that of the size of sulfide is 0.4. Size of zinc is right smaller than the size of anion. We all know cations are generally smaller than anions. Now, if you see, this is what it is, present zinc sulfide structure. The question is, right, this radius ratio lies between what to what? Radius ratio lies between 0.225 to 0.414. That means the radius ratio indicates zinc occupies tetrahedral void, and we know tetrahedral void is a speciality of FCC and HCP, but we are going to take cube as a standard. That means FCC. That means somebody should be making FCC. Who is that somebody who is making FCC? Sulfide ions. So, remember, who is making sulfide ions is making FCC and its rank is 4. When somebody says rank is 4, remember it makes up 8 corners and 6 face centers. Are you able to see 8 corners? 8 corners and 6 face centers. These are the face centers which I am shading it with lines. These are sulfide ions, and apparently they contribute for 4 sulfide ions per unit cell. So, zinc must be present in tetrahedral void as per radius ratio. Now, number of tetrahedral voids in unit cells are 8, but we know there are 4 sulfide ions. So, how many zinc ions should be present so as to have a charge of 0? Can you guess? Yes, you are right. 4 zinc ions should be present, but tetrahedral voids are 8. Zinc is present in tetrahedral void, but as for charge cancellation, there should be only 4 zinc ions. That means all tetrahedral voids, if they are occupied, charge will not be balanced. That means total charge on zinc will be 16, but total charge on sulfide ion is 8. So, how many zinc ions should be present? Answer is it should be corresponding to plus 8. That means only 50% space should be occupied. 50% of the space should be occupied. So, zinc ions do not occupy tetrahedral void. That means they occupy only 50% of tetrahedral void. What do you mean by 50% of tetrahedral void? They occupy alternate tetrahedral voids. So, thus number of tetrahedral voids occupied by zinc are 4. That means zinc is 4, sulfide is 4, therefore formula is zinc sulfide. So number of formula unit is 4, so we say rank for zinc sulfide is 4, if you understand. So zinc occupies tetrahedral void, and you know tetrahedral void coordination number is 4, and we know sulfide is surrounded by 8 tetrahedral void, but out of which only 50% is occupied. That means only 4 zinc ions surround sulfide ions. Therefore, coordination number for sulfide is also 4. Are you understanding it? So, if you go back and check all the data and you understand zinc sulfide, then go back and learn sulfide ions makes up FCC. That means its rank is 4. That means 8 corners and 6 face centers. Where is zinc? Zinc is present in tetrahedral void. But why? Because the radius ratio, right, forces it to occupy tetrahedral void. Is it present in all the tetrahedral void? No, it is present in 50% of tetrahedral void. Tetrahedral voids are 8 in number. 50% of that is 4. That means, right, one unit cell is made up of 4 zinc sulfide units. Are you understanding it? So, zinc, where is zinc present? If this is body diagonal, on body diagonal, you know there are 2 tetrahedral voids, but one is empty and one is filled, because only 50% is filled. So, remember, only 50% is filled. So, this was all learning about sodium sulfide, not sodium sulfide, sodium chloride, rock salt structure, and zinc sulfide. Now, remember, zinc occupies tetrahedral void. So, tetrahedral void, what is the coordination number of tetrahedral void? 4. So, what is the coordination number of zinc? 4. Sulfide, any sphere is surrounded by 8 tetrahedral voids, but only 50% is occupied. That means it is surrounded by only 4 zinc ions. So, what is the coordination number of sulfide ions? 4. Such a type of solid is called as 4:4 ionic solid. So, we will stop here only. We will continue in the next. We come to the next part of types of ionic structure, in which we are learning diamond. Now, diamond is not ionic. It is a covalently bonded compound. You call it as covalent solid. Still, we are learning along with ionic structure because it shares similarity with one of the ionic structure. With whom it shares similar structure? Zinc sulfide. If you remember, in zinc sulfide, sulfide ions were making up FCC. That means 8 corners, 6 face centers, and zinc ions were occupying 50% of tetrahedral voids. That means alternate positions were filled by zinc ions. Diamond is very similar to zinc sulfide, everything same. Only the difference that we have is all the positions are actually occupied by carbon atoms. So, whether you say sulfide or whether you say zinc, all the positions are occupied by carbon. That means you have to imagine in the place of sulfide carbon. That means it is 4 in number. In place of zinc also you have to imagine carbon, and 50% of tetrahedral void, 4 in number. That means total number of carbons are 8. That means rank of diamond is 8 rank. That means it is made up of 8 carbon atoms in one unit cell. So, if you check this shape, it tells you these positions, which are 8 corners, are occupied by whom? Yes, they are occupied by carbon. And who occupies the face center? Who occupies the face center? Again carbon. And who occupies this tetrahedral void? Again carbon. If you know, right, there are 2 tetrahedral voids on one body diagonal, but one is occupied, other is empty. That is what you mean by 50% of tetrahedral void. So, rank of diamond is 8, of which 4 make up corners and face centers, that is FCC, and remaining are 50% of tetrahedral voids. So, there are 8 carbon atoms per unit cell. and if you do trigonometric calculation, then we realize r plus r is equal to a root 3 by 4. That is what you come to know. That is what is the calculation. Now, that means r is equal to a root 3 by 8. If you calculate packing fraction, if you remember packing fraction is z multiplied by volume of the spheres occupying divided by volume of the cube. So, you know the sphere is 4 by 3 pi r cube z into a cube. Now, if you put the value of z as 8 and you calculate all these things, then packing fraction will come out to be 0.34. So, you have to remember diamond has packing fraction of 0.34, that means 34% of the space is occupied and remaining is empty. Conclusion about diamond is diamond rank is 8. There are 4 present at FCC and 4 are present in tetrahedral void. And you should remember R, right, that is the radius of the carbon sphere is a root 3 by 8, where a is the edge length and packing fraction is 0.34, and you should know diamond is similar to zinc sulfide. Only thing is, in the place of zinc as well as sulfide, who is present? Answer is carbon. That's what is information about diamond. So, if you go back and learn, this is what was a discussion about diamond. So, rank is 8, r plus r is equal to a root 3. If you check distance between the corner and the tetrahedral void, this distance is r, and r, that is nothing but a root 3 by 4. You should know tetrahedral void is at a distance of a root 3 by 4. That is what is the logic. And then you do all the calculations, your packing fraction will be 0.34. So, that was a discussion about diamond. Fluoride structure, right, where the example is CF2. It got the name as fluoride because it was containing fluorine in it. Now, in calcium fluoride, if you imagine fluoride makes a FCC, it will be 4 in number. Then either the calcium will occupy octahedral void, then it will be 4 in number, or it will occupy tetrahedral void, and that will be 8 in number. Now, you imagine the first case, fluoride makes up FCC 4, calcium makes up octahedral void 4, then there will be no charge cancellation. No charge cancellation, because the total charge in this case will be plus 8, total charge in this case will be minus 4, and the total unit cell charge will be not 0. So, that means this possibility is not there that calcium occupies octahedral void. Now, imagine calcium occupies tetrahedral void. Imagine occupies 100% tetrahedral void. So, it will be 8 in number. If it is 8 in number, charge will be plus 16, and fluoride still is minus 1. So, till this also there will be no charge cancellation. So, whether calcium occupies octahedral void or whether calcium occupies tetrahedral void, charge cancellation doesn't happen. That means now you have to have a unique other way of understanding. So, here we reverse our understanding and we imagine that calcium occupies or makes up FCC. When I say calcium occupies FCC, that means it makes up 8 corners and 6 face centers as shown in the diagram. 8 corners, are you able to see small calcium ions making up 8 corners and 6 face centers. Now, I am shading all of them, all calcium ions. That means what is calcium in number? Calcium in number will be 4. Now, how much should be fluoride in the number? Think, fluoride should be such that the charge should be 0. You are correct. It should be 8. We know octahedral void are 4. Tetrahedral void maximum are 8. That means, alright, fluoride should be present in tetrahedral void, and that too 100% tetrahedral void. Are you able to see this? Right, spheres, these spheres which are black in color are fluoride ions and they are tetrahedral voids. So they occupy tetrahedral voids. So remember, the smaller green color spheres are calcium and bigger sphere are fluoride. And where are fluoride present? They are present in tetrahedral voids, and they are occupying 50% tetrahedral voids or 100% tetrahedral void. They are occupying 100% tetrahedral void. Then only charge balances will take place. Remember that. That means there are 4 calcium ions, 8 fluoride ions. Charge is 0. That means 4 calcium fluoride units. That means the rank of a unit cell is 4 calcium fluoride units. 4 calcium fluoride unit, that means 4 calcium ions and 8 fluoride ions. So calcium occupies FCC is 4, hence formula unit calcium is 4, fluoride is 8, therefore the formula matches as CaF2. That's what you should know. Fluoride occupies tetrahedral void and therefore coordination number will be what? Coordination number will be 4. So coordination number for any tetrahedral void is 4. So coordination number for fluoride is 4. So you are able to understand the next number is for fluoride. Second number is always for anion. And any sphere is surrounded by how many tetrahedral void? 8. So calcium is surrounded by how many tetrahedral void? 8. So coordination number of calcium is 8. Coordination number of calcium is 8. Are you understanding it? Therefore, the solid is called as 8:4 solid. So, summary again, calcium occupies which position? Calcium occupies FCC. That's quite different. We are for the first time considering cation making up a lattice. And where is fluoride present? We are first time imagining it is occupying tetrahedral void. How much tetrahedral void? 100% tetrahedral void. But why? For total charge cancellation to be 0. What is the number of calcium? 4. What is the number of fluoride? 8. What is the coordination number of fluoride? 4. What is the coordination number of calcium? 8. And how many formula units of calcium fluoride are present? 4. That was about the information called as fluoride structure, where the example is calcium fluoride. And from this we go to the next ionic structure, AntiFluoride. Now the word AntiFluoride means the structure and the arrangement will be reverse of fluoride. If you remember, in fluoride what we saw, calcium cation making up FCC and fluoride making up 100% tetrahedral void. Here exact reverse will take place. That means in place of calcium there will be oxide, in the place of fluoride there will be sodium. Please keep a look at it. So what is, right, where is oxide present? Oxide is making up FCC and therefore 4 in number. So what is the total charge present? -8. And where is sodium present? 100% tetrahedral void. What is the total charge present? +8. So total charge here is -8, 4 multiplied by -2, a -8, 8 multiplied by +1 +8. What is the total charge? 0. Any unit cell should have 0 charge. So oxide makes up FCC. Somebody says FCC means 8 corners and 6 face centers. And where is Na plus present? Tetrahedral void. It should be present in 100% tetrahedral void so as to have charge cancellation. So 8 sodium, 4 oxide, therefore formula will be Na2O. So number of formula units is 4. We say rank is 4. So Na plus occupies tetrahedral void. If it is occupying tetrahedral void, anyone who is occupying tetrahedral void will have coordination number of 4. So 4 is the coordination number of Na plus. Where is oxide ion present? Oxide ion is present as a sphere. Any sphere is occupied by 8 tetrahedral void. That means oxide is surrounded by 8 Na plus, and Na plus which is present in tetrahedral void is surrounded by 4 oxide ions. 1 Na plus is surrounded by 4 oxide ions, and 1 oxide ion is surrounded by 8 Na plus. Conclusion, you should remember tetrahedral void coordination number is 4, octahedral void coordination number is 6. Any sphere is surrounded by 6 octahedral void. Any sphere is surrounded by 8 tetrahedral voids. Now this is an extra information about the distance. That's not much important for us. That was about anti-fluoride. The entire arrangement of anti-fluoride was a reverse of fluoride. Therefore, the name came up as anti-fluoride. The next structure that we like to understand is cesium chloride. In cesium chloride, the radius ratio is found to be 0.93. Now, you know this radius ratio lies between 0.732 to 1. That means our cation is present in cubic void. If you are saying your cation is present in cubic void, remaining are making up SCC. That means rank is 1. So, how many chloride ions are present? 1. 1 chloride ions that are making up 8 corners. You should know 8 corners contribute as 1 chloride ion for SCC, and cesium occupies cubic void, therefore its rank is 1. That means 1 cesium ions, 1 chloride ion. That means 1 cesium chloride. That means formula unit will be cesium chloride. Number of formula unit will be 1. Since cesium occupies cubic void, its coordination number will be 8. And we know any sphere is surrounded by how many cubic void? 8. 1 here, but this sphere is present in 8 cubes, and each cube will have 1 cubic void. So, coordination number of chloride is 8. Therefore, the solid got the name as 8:8 solid. So, remember, chloride makes up SCC, therefore 1. Cesium is present as cubic void, or you can call it as body center, means 1. If you take cesium chloride, then it is BCC. You are considering simple cubic crystal and cubic void occupied. If you see the entire structure, if you include cesium chloride, it is BCC. But if you say only chloride, it is SCC, and the rank is 1. So, right, cesium chloride rank is 1. That means you should remember BCC are of 2 types. If they are metallic solid, rank is 2. If they are ionic solid like cesium chloride, rank is 1. Rank is 1. This is an extra formula for you to know. So, that was about cesium chloride. So, we stop here. In types of ionic structure, under that, effect of pressure and temperature on coordination number of ionic solids. Now, on increasing pressure, what exactly happens? If you have such type of an arrangement, imagine such type of an arrangement, and you increase the pressure on the solid. When you increase the pressure, then the other ions also are forced in. When other ions are forced in, what do you feel? On increasing the pressure, ions come closer, and therefore number of red atoms which can be fit around the sphere will increase. Therefore, coordination number will increase. So, what is the effect of pressure? As pressure increases, coordination number increases. So, a 4:4 solid will become 6:6 solid. Remember that. Now, right, when you decrease pressure, what do you expect will happen? Will coordination number decrease? Answer is nothing will happen, because solids are unaffected By decrease in pressure. Once you have powdered a solid, can the solid go back to crystalline form? No. So you can't remove the pressure. You can add pressure and remove pressure for gas, but you can't remove pressure for solid. So reverse will not happen by removal of pressure. So it is only one way. What is the effect of temperature? Imagine if particles are like this, are arranged like this, and if you heat, can I say the particles will go away? Will go away. So what do you expect? There may be a 6:6 solid can become 4:4 solid, like this. So what will happen? 8:8 solid can become 6:6 solid, or 6:6 solid can become 4:4 solid. So what is the effect? If pressure increases, coordination number increases. If temperature increases, coordination number decreases. So remember, when you pressurize, particles will be forced closer, closer, closer. Coordination number will increase. If you increase temperature, particles will go away, away, away. So coordination number will decrease. So that is the effect of pressure and temperature. You got this? If you decrease temperature, can coordination number again become 8:8? Answer is yes, because heating and cooling is possible for solids. But pressure, the effect is only one way. So if temperature is increased, coordination number decreases. If temperature decreases, coordination number can get increased. So that was the effect of pressure and temperature on coordination number. Next, density formula remains same that you learned in metallic solid. Z multiplied by m divided by a cube into Na. That was a formula where D stands for density, m stands for molar mass of an ionic compound. So if you are taking molar mass of NaCl, then molar mass of NaCl will be 58.5. Similarly, if you take molar mass of cesium chloride, it will be 133 for CCF, 35.5, then 168.5. This is how molar mass will be calculated for ionic solid. This is rank. If you know what is a rank for NaCl, a rank for NaCl is 4. What is a rank for zinc sulfide? If you remember, it is 4. What is a rank for calcium fluoride? It is 4. What is a rank for sodium oxide? It is 4. What is the rank for cesium chloride? That's the unique one, 1. And what is the rank for diamond? It is 8. That's the unique one. That were all the ranks. And A stands for edge length of that ionic solid. Na stands for Avogadro number, that is 6.022 into 10 to the power 23. So same formula, and you should remember cesium chloride, it is 1. Now if you take FCC, there are two types of FCC, metallic and ionic, where metallic solids have rank of 4 and all ionic solids with FCC are also 4. So we don't worry about FCC whether you are dealing with metallic solid or ionic solid. Remember, in metallic solids all the spheres were of the same size, and for ionic solids spheres are of different sizes. Remember that spheres are of different sizes. Diamond, although we learned along with ionic solid, it's not an ionic solid. We learned because it was similar to zinc sulfide. But if you see BCC, there are two types, metallic BCC, where spheres are of the same size, and ionic BCC, there is only one example, cesium chloride, where rank is 1 and here rank is 2. So remember, BCC metallic solid rank is 2, BCC ionic solid rank is 1.